Assalamu alaikum. In this presentation, I am going to prove that weak induction and strong induction, they are equivalent. I am Mohammad Tawqid Hamid from GUID CSE 18. So let's start. Okay, so in terms of induction, we have two types of inductions. The first one is the weak induction or the regular induction, and the second one is called the strong induction. In weak induction, what does it mean? If for any statement involving a positive integer n, the following are true. The statement holds for n equal to 1. Whenever the statement holds for n equal to 1, it must also hold for n equal to k plus 1. So if the statement holds for n equal to k, and we can prove from here that the statement also holds for n equal to k plus 1, then we can say that the whole statement is true for any values of n. So this is the principle of weak induction. Here we have two hypotheses. We have to prove the base case, and we have to assume that this statement is true for n equal to k, and from there, we have to prove that the statement is true for n equal to k plus 1. Okay, so next here comes the principle of strong induction. The principle of strong induction also states that we have to first calculate the base case. If we can prove the base case, then we should go to the next step. The next step is whenever the statement holds for all n is less than or equal to k, it must also hold for n equal to k plus 1. So whereas we took in weak induction that the statement is true for n equal to k, in this strong induction we assume that the statement is true for all values starting from the base point up to k are all true, and from that we deduce if we can show the value is true for n equal to k plus 1. And if this two statement holds, then we can say that the statement is true for any values of n. So now we will prove that strong and weak induction are equivalent. That is, we can prove strong induction principle from weak induction principle and vice versa. And at the end of this lecture, I'm going to show an example where we will prove that statement using both strong and weak induction. So case 1, if weak induction is true, strong induction is also true. So for case 1, we assume that the weak induction principle is valid. And from that, we are going to prove that strong induction is also true. So let's start. By the principle of weak induction, if in a statement P of n, the following are true. We discussed this earlier. P of 1 is true. This is the base case. If P of k is true, then P of k plus 1 is true. And if these two statements holds, then we can say that P n is true for all values of n. So we assume that weak induction is true. So P of n can be proved by weak induction. For proving strong induction, we are going to modify our statement a little bit. We define a statement Q of n be for all x less than or equal to n, P of x. So what we did is we replaced the initial statement P of n with Q of n and some modifications. So what Qn says that if you have a value, suppose the value of n is 3. So it states that for all values less than or equal to 3, P of that value is true. So we are assuming that for all values, x is less than or equal to the number replaced in the function of q here, P of that number is true. So this is our statement. A closer look reveals that this is essentially the hypothesis of strong induction. And we know that in case of strong induction, our hypothesis is our statement is true for all values starting from the base up to k. This is our hypothesis. And from that, we need to prove if it is true for k plus 1. So the modified statement here is actually the hypothesis of strong induction. So we will prove this statement using weak induction because we have assumed that weak induction is true. We are not yet sure if strong induction principle is valid or not. We are going to deduce that from this statement. Okay. So let's go in an inductive manner. In step 1, for n equal to 1, the statement is for all x less than or equal to 1, P of x. Okay. So we are saying that our base case is n equal to 1, and if we place 1 here, so the only x is less than or equal to 1 in our case is 1 because we are working with positive integers. So x is less than or equal to 1 means we have on one case x is equal to 1. So we are saying that from 1, we have assumed that P of 1 equal to 2. So if P of 1 equal to 2 here, so Q of 1 also be true. So this proves our base case. Now let's go to the next step. For n equal to k, we suppose that this statement is true. So for n equal to k, the statement is for all x less than or equal to k, P of x. So we assume this statement is true. That is, P of k is true. From here, we need to prove the statement for n equal to k plus 1. Okay, so let's go to the step 3. In step 3, we are going to work with n equal to k plus 1. So in step 2, we have assumed that the statement is true for n equal to k. So in step 3, we are going for n equal to k plus 1. So for n equal to k plus 1, the statement is for all x less than or equal to k plus 1, P of x. Okay, so here we have two cases. X is less than k plus 1 and x equal to k plus 1. So this is essentially less than or equal to means. So we have assumed that for x equal to k plus 1 and x less than k plus 1, we have to prove the case. In the first case, if x is less than k plus 1, this means that x is less than or equal to k. By step 2, we have assumed that this is true. So our first case is good. Now we have to prove for x equal to k plus 1. In the second case, x equal to k plus 1, with that statement becomes for x equal to k plus 1, P of x. And this is, we need to show P of k plus 1 is true. So from step 2, we know that P of k is true, right? From this step, we know that P of k is true. And as we have assumed that our weak induction is true, so the hypothesis of weak induction is also true. So if P of k is true, then P of k plus 1 is also true. So from step 2, we know that P of k is true. So from our second hypothesis of weak induction, we can deduce that P of k plus 1 is also true. So now we have shown that n equal to k plus 1, or if equal to n equal to k plus 1, Qn is true. So in these 3 steps, assuming our weak induction principle holds, we have proved that our statement Q of n for all x is less than or equal to n P of x is true. So this completes our proof. So what we have proved? We have proved that P of 1 is true. Then if for all x is less than or equal to n, Px is true. So by this statement, we assumed and proved P of n plus 1 is also true. So these 2 statements are essentially the statements of strong induction. So these prove the statements of strong induction. Thus, if weak induction is true, then strong induction is also true. So from here, we have proved strong induction by assuming weak induction is true. So our first proof is done. Next, we're going to next step. That is, if strong induction is true, weak induction is also true. This is a bit easier to intuitive than the previous one. By the principle of strong induction, if in a statement P of n the following are true, P of 1 is true. So base case, and if the statement holds for all n is less than or equal to k, then it must also hold for n equal to k plus 1. And if these 2 statements hold, then P of n is true for any values of n. So these 2 lines are the hypothesis of strong induction. So we are assuming now that the strong induction is true, and from that we're going to prove that weak induction is also true. So in step 1, we take n equal to 1. So we know that P of 1 is true, which is the base case and proved by 1, no doubt. In step 2, we are assuming that n equal to k. So we assume this statement is true. We need to prove n equal to k plus 1 is also true. So as this is weak induction, we need to prove weak induction. We are assuming only n equal to k is true, not all values from the base up to n. We are assuming only the value n equals to k, and we assume that this statement is true. And from that, we need to prove that n equal to k plus 1, this statement is also true. So in step 3, we take n equal to k plus 1. Okay. So in step 2, we assume that for n equal to k, the statement is true. From this equation 2, we know that if the statement holds for all values of n is less than or equal to k. So as strong induction is true by our claim, so n is true for any values less than or equal to k. So here we have taken the value of n to be k. So if n is true for any values less than or equal to k, so of course for equal to k, this is true. So if this is true, then k plus 1 is also true by 2. So which predictive quantity is that the statement also true for n equal to k plus 1. And yes, this completes the proof. We have proved the base case. We have assumed that the statement is true for n equal to k. And from that, we have proved that the statement is also true for n equal to k plus 1. And this is the principle. So we have showed that the principle of strong induction, it holds. The principle of weak induction is also true. So from these 2 proofs, we conclude that strong induction and weak induction are equivalent. So in the first place, we have proved that if weak induction is true, then strong induction is also true. And in the second step, we have proved that if strong induction is true, then weak induction is also true. So from this, we have proved that strong induction and weak induction are equivalent because they are birelated statements. Okay, so here we'll see an example, a statement that we will prove in both manners, in weak induction and strong induction. So our statement is that in a tree with n vertices, we have n minus 1 edges. So this is a very familiar proof from graph theory. We are going to prove it by both strong and weak induction. So let's move on to strong induction. In step 1, we take n equal to 1. It means that we only have one vertex in our tree. If we have only one node in the tree, it is obvious that there is no edge in our tree. Yes, we have only one node, there is no edge in our tree. So that the number of edges only 0, which is n minus 1 or 1 minus 1. This proves our base case. Now let's move on to step 2 for n equal to k. So in this case, in our graph, we have k nodes. We assume that for all values n less than or equal to k, the statement is true. That is, in a tree with less than or equal to k nodes, we have k minus 1 edges. Because as we're working with strong induction, if we take n equal to k for true, then it is true for any value starting from the base case up to n equal to k. So from this step, we need to prove that the statement is true for n equal to k plus 1. So we see the step 3 next. We take n equal to k plus 1. In this case, our tree contains k plus 1 nodes. So if n equal to k plus 1, our tree has k plus 1 nodes. We know that every edge in a tree connects only 2 nodes. So every edge in a tree connects only 2 nodes. Thus, if we remove one edge from the tree will be divided into 2 disconnected components. By definition, these 2 components will each be tree individually. So it's very clear that if we divide a tree just by removing an edge, the 2 components will also be a tree. So let us assume that the first component A, so we're assuming that with the 2 components we got by removing the one edge is component A, component 1 and component 2. So first component has A nodes and second component has B nodes. As we have only 2 components, the sum of A plus B equal to K plus 1. So actually we divided our tree with K plus 1 nodes into 2 components, A and B. So if we add A plus B, we will get K plus 1. And from here we can also deduce that A is less than or equal to K and B is less than or equal to K. So our resulted 2 graphs, the node of those 2 graphs will always be less than or equal to K. So by principle of strong induction that we discussed earlier, we can say that the two individual components hold the property of our statement. So the first component with A nodes will have A minus 1 edges, and the second component with B nodes will have B minus 1 edges. We also have one edge E that was removed to separate the two components. Okay, so that the total number of edges in this complete tree will be A minus 1 for the first component, B minus 1 for the second component, and the 1 for that we have removed. So if we add all this, we will get K. So this completes our proof. From this step, we showed that this in a true, and this is proof for K n equal K plus 1. So thus any tree with n nodes has n minus 1 edges. So from strong induction, we have proved that if we have a tree with n nodes, we will have n minus 1 edges. So let's prove it by weak induction. And similarly, we take step 1 as n equal to 1. If we have only one node in our tree, it is obvious that there is no edge in our tree, thus the number of edges 1 minus 1 equal to 0. So this proves our base case. Let's move on to step 2. In step 2, we have n equal to k. So we assume that for n equal to k, our statement is valid. That is, in a tree with k nodes, we have k minus 1 edges. So for n equal to k, we took this true. So from this, we need to prove the statement for n equal to k plus 1. So in step 3, we assume that n equal to k plus 1. So now we have k plus 1 nodes in our tree. And from the properties of a tree, we know that a tree must contain at least one node with degree 1. So if we have a tree, it must have a node with degree 1. So let's assume that node to be V. So that one node that has 1 degree, let's take that to be V. And the only edge that is connecting the node V to the rest of the tree is E. So the 1 degree node is connected to the rest of the graph by the edge E. Now we subtract this node from the tree. Okay, so this will also remove edge E from the tree. Thus, the remaining tree is now containing k nodes. From step 2, we deduce that this tree with k nodes has k minus 1 edges. That was our hypothesis. Okay, so now we again add the subtracted node and the edge to the tree with k nodes. Now we have the total number of nodes equal to k plus 1. Okay, so now we are adding those 1 degree node to the rest tree. So now we have total number of nodes equal to k plus 1. And by the property we mentioned above, we have subtracted only one edge because we have subtracted the node with degree 1. So we have actually subtracted one edge. So now the total number of edges will be 1 higher than the separated tree. So the total number of edges equal to k minus 1 plus 1 equal to k edges. And we proved that for a tree with k plus 1 nodes, we have k edges. And this completes our inductive proof. So thus, for any tree with n nodes, we have n minus 1 edges. So we have proved this statement by both strong and weak induction. So this ends my presentation. Thank you all. Assalamu alaikum.